Okay, so today we are going to continue with optimization. Let me see something first. Okay. So in Calc 1, we saw that it's important sometimes to know where the maximum and the minimum of a function are. So if it's our function and we would like to find its minimum or its maximum, what we ended up doing is we looked at f prime of x and we set it equal to 0 to find the critical points. And then we use the second derivative. Now, does anyone remember, does the second derivative, if the second derivative is bigger than 0, is this a minimum or a maximum?
A minimum if it's greater than 0.
Yes, so this would be a minimum, and if the second derivative is less than 0, this would be a maximum. And we also saw in Calc 1 that if you want to find global minimums and maximums on an interval, then what you end up doing is you look for the critical points inside of the interval, and you also look at the points on the boundary of the interval. So in this case, for example, the global minimum will actually be this point, and the global maximum will actually be this point. So we want to do something very similar, but in 3 dimensions. So first, in 3 dimensions, if we have some function and we want to find its minimum or maximum, then at this point, at the minimum or maximum, the derivative both in the x and y direction will be 0. So instead of only taking the derivative in 1 dimension, which we only have 1 dimension over here, we end up taking partial of f with respect to x, setting that to 0, taking partial of f with respect to y, setting that to 0, and then solving these for x and y to find the point where the minimum exists. Or we can also look at this in terms of the gradient of f of x, y, and setting that to the vector 0, 0. So the notion of a local max and a local min are pretty simple. It's just the points, a point such that for the local maximum point such that all the points near it are less than it. Same thing with local minimum, all the points near it are bigger than it. And like I said, in order to have a critical point, you need that the partial with respect to x is going to be 0, the partial with respect to y is going to be 0, or they don't exist, but we're not going to focus on that case. So the same way for 1 dimension, we have the local maximum, the line, the slope of the line will be 0. Over here, the slope of the tangent plane in both directions will be 0, and that's how we are going to find critical points. So let's do an example. They tell us function f of x, y is equal to 11x squared. So f of x, y is equal to 11x squared minus 2xy plus 2y squared plus 2y squared plus 3y. and they say it has one critical point, and they ask us to find that critical point. So the partial of this function with respect to x is going to be equal to 22x minus 2y. And we set this equal to 0. The partial of f with respect to y is going to be negative 2x plus 4y plus 3. So now we can use the first equation. Oh, and again, we set this equal to 0. We can use the first equation to say that 2y is equal to 22x, or in other words, y is equal to, y is going to be equal to 11x. So now we can use this to solve for our y by plugging into the second equation. So that will give us negative 2x plus 4 times 11x plus 3 is equal to 0. Okay, so we are going to get negative 2x plus 44x plus 3 is equal to 0. Or we are going to have 42x is going to be equal to negative 3, or x is going to be equal to negative 3 over 42. Sure. 1. Good. So that's our x. Now our y is going to be 11 of those. So y is going to be negative 3 times 11 over 42. So these are critical points. So our critical point is negative 3 over 42 and negative 33 over 42. Any questions about this? Okay. The next example requires a calculator, so I'm going to skip it. Okay. So now the same way in Calc 1, we had the second derivative test. In Calc 2, we use this thing d, which is going to be partial of f with respect to x twice times partial of f with respect to y twice minus partial of xy squared. And we're going to use this d to figure out whether we have one of three options. Either we're going to have, so here's that d. Either we're going, so in Calc 1, there are only two options. We can either have a maximum or a minimum. But in multivariable calculus, we can either have a maximum, a minimum, or a saddle point, where in one direction we have a minimum, but in the second direction we have a maximum. So in order to figure out which one of these cases we have, the same way in Calc 2, we use the second derivative. And if it's bigger than 0, this is a min. And if it's less than 0, it's a max. In our case, we're going to use this d to figure out what situation we're in. So if the d's are positive, then if the second derivative is positive, we have a minimum. Same thing with Calc 1. If the second derivative is positive, we have a minimum. If the second derivative is negative, we have a maximum. But if the d is negative, we have a saddle point. So if the d is positive, you look at the f with respect to x twice to see what's going on. And if it's negative, you know that we have a saddle point. So any questions about this? And if d is equal to 0, we don't know. It's inconclusive. So let's try an example. So they say apply the second derivative test, find the critical points of this function, and analyze them using the second derivative test. So our function is f of xy is equal to x squared plus y squared, x squared plus y squared times e to the negative x times e to the negative x. Okay, so let's first find the critical points. The partial of f with respect to x is going to be equal to, x squared plus y squared times negative e to the negative x plus 2x e to the negative x, which is going to be equal to negative x squared minus y squared okay, negative x squared minus y squared plus 2x e to the negative x. And we want to set this equal to 0. Any questions so far? Okay, the partial of f with respect to y is going to be 2y to the negative x, 2y to the negative x. And we also set this to 0. So from the second equation, we get that y is equal to 0. So that's what we get from the second equation. From the first equation, then, we get negative x squared plus 2x times e to the negative x is equal to 0. So so the e to the negative x doesn't matter. So we get negative x squared plus 2x is equal to 0. So we have two options, either x is equal to 0, one option, or x is equal to 2. That's the second option. So our critical points are going to be 0, 0, and 0, and 2, 0. Any questions about this? Okay, so now we know where our critical points are, and we want to know whether they're minimums, maximums, or saddle points. So our D is equal to the partial of f with respect to x twice times partial of f with respect to y twice minus partial of xy squared. So the question is, what is our partial of f with respect to x twice? So we're going to go here, and we are going to get negative, so let's just do negative x squared minus y squared plus 2x times negative e to the negative x plus negative 2x plus 2 times e to the negative x. And this is going to be equal to x squared plus y squared minus 2x minus 2x plus 2 times e to the negative x, which is going to be x squared plus y squared minus 4x plus 2 e to the negative x. So that is our partial with respect to x twice. Let me just check. y squared negative 2. Okay, good. Now let's look at the partial with respect to f twice. So partial f with respect to y twice is going to be, so now we're looking at this over here. So that's going to be 2e to the negative x. 2e to the negative x. Okay, great. And then the last one that we want is the partial of f with respect to xy, which is going to be negative 2y e to the negative x. Negative 2y e to the negative x. Negative 2y e to the negative x. Great. So we have our last one. Any questions so far? So now we need to plug in our points. So our d is going to be, again, fxx at 0, 0 times fyy at 0, 0 minus fxy at 0, 0, which is going to be, so from here we're going to get zeros, 2, so 2. So that's going to be 2 times, and then f of y, we plug in 0 for y. No, we plug in, so that's 2 again. Good. And then minus, oh, and this thing is squared. Minus, and then we plug in a 0 for y, so minus 0 is equal to 4. Okay, question. If the d is 4, what are the different options that we get?
A min or a max?
Either a min or a max. So then we look at the partial of f with respect to x twice. We see that it's positive, so we know that this is a min. Okay, let's do the second one. So for the second one, d of 2, 0, right? Yeah, 2, 0. D of 2, 0 is going to be one second. So we're going to have 4 minus 8 plus 2 e to the negative 2 times, and what is this? This is going to be negative 2. So negative 2 times, and then for the second one, we're going to have 2e to the negative 2, 2e to the negative 2 minus 0 squared. So this is going to be negative and whatever. So this is less than 0. So we have a saddle. Any questions about this? Okay. So they got the same result, local min, saddle. You continue. So here's another example, which I'm going to skip. And here's an example of when the second derivative fails. So your d would be equal to 0. And that's what they get. D is equal to 0. No information. Okay. So now we're going to move on to the next part, which is global extrema. So the same way in Calc 1, we had the difference between a local min and max. So these are local min and max, but there isn't a global min and max over here because you can continue going up or down. But if we created a restriction, if we restricted to some domain, then we would have a global min and max, and the max would be here, and the min would be here, or sorry, here. Maybe actually this would be the min. It's hard to tell, but we would have to check. So too, in our case, we might not necessarily have a global min and max. So if we have something like this, then the minimum and the global minimum would be here, but there isn't a global maximum. But if we restrict ourselves to some domain, let's say a disk, so then we're only dealing with the part of the function below this part, and then we would have a max, and that would be all these points on the disk. And that's what we want to do now. We want to be able to find global mins and max with some restriction. And the way to do that is pretty simple. We look for the critical points on the interior, and we make a list of them. All the critical points on the interior, again, we take the gradient of f and set it equal to 0, 0. And we look at the boundary points, so all the boundary points of our domain, and we try to find critical points on those boundary points. And we'll see that that boils down to a Calc 1 problem. And we collect all these critical points, we plug them into our function, and we find the global minimum or maximum. So let's do an example. Here's an example. So find the maximum and minimum values of the function. So f of xy is equal to 2x plus y minus 3xy. 2x plus y minus 3xy on the domain, which is the set of all points xy, such that x and y are between 0 and 1. So we're on the unit rectangle square. 0 is less than x, whatever, less than or equal to 1. 0 is less than or equal to y, less than or equal to 1. So in this case, the first thing that we would want to do, so let's first make a picture of the domain. It's always useful to make a picture of the domain in this case. So here's my x, here's my y, and this over here is my disk. So first I want to find the critical points in the interior. And the way to do that is by taking f partial of f with respect to x, which is going to be 2x minus 3y, and setting this equal to 0. Taking partial of f with respect to y, which is equal to 1 minus 3x, and setting this equal to 0. So we will get from here that x is equal to 1/3. And so our y, so we have that 3y is equal to 2, one second. 3y is going to be equal to 2x. So that's 2 times 1/3. Give me 1 second. 2/3. I think I did not take this derivative correctly. Let's see. Partial of f with respect to x is going to be not 2x, 2. Perfect. Okay. Okay. So from here we get, so we get that y is equal to 2/3. Any questions about this? So our critical point in the interior is going to be 1/3, 2/3. So let's make a table and keep track of them. So here's my x, y. Here's my f of x, y. And the first critical point that we found is the point 1/3, 2/3. And f of 1/3, 2/3 is going to be equal to 2 times 1/3 plus 2/3. So 2 times 1/3 plus 2/3 minus 1 times 2/3 minus 2/3, which is equal to 2/3. So the value over here is 2/3. But now there might be critical points on the boundary that we missed. So we need to look at the boundary. So let's start with this boundary over here. It's the boundary where y is equal to 0. So if we want to evaluate that boundary, what we can do is we can look back at our function. So let me rewrite it. F of x, y is equal to 2x plus y. So f of x, y is equal to 2x plus y minus 3xy. So then we can plug in a 0 for our y, and we get f of x, 0 is equal to 2x. And now this is how the function looks on this boundary, because that y is 0 over here. So now in order to find the critical points on that boundary, we just need to take the derivative of x0, and that's going to be 2, which is never equal to 0, so it does not have any critical points. But we do have to keep track of these points, the boundary of the boundary, because that's the same as when we have one dimension. So our boundary was this green part, our function maybe looks something like that. And then we need to also plug in these points to see what happens. So what are those points? So those are critical points, so we can add them to the list. It's the point 0, 0, and the point 1, 0. And the results would be 0, and 1, 0 will get us to 1. Okay, now let's continue with this boundary over here. So that is x is equal to 1, y is 0. So f of 1, oh sorry, and y is y. Y just stays y, right? X over there is equal to 1, y varies. So now this is going to be 1 plus y minus 3y. And so now the derivative, f prime of y, 1y, is going to be 1 minus 3, which is equal to -2, which does not equal 0. So once again, we do not have critical points on this boundary. But we need to evaluate this point over here, which is the point 1, 1. So that would be the point 1, 1. And for that point, we are going to get 2 plus 1, which is 3 minus 3. So we get 0. Any questions so far? Okay, so let's continue with this boundary over here. This is the boundary x, y is equal to 1 and x varies. Y is equal to 1 and x varies. So that's f of 1x, which is going to be x plus 1 minus 3x. So the derivative is going to be 1 minus 3, which again is 1 minus, yeah, which again is -2.
Didn't you drop 2 on your first x? Isn't it supposed to be 2x?
Yeah, maybe I'm not putting things in. Yeah, 2. Thank you. 2. So here's 2. whatever. Here's 2. So we have -1, which again is not equal to 0. So we don't have a critical point on this boundary. So we don't have a critical point on this boundary, but we need to plug this point in. And this is the point where x is equal to 0 and y is equal to 1. So if y is equal to 1, then we will get 1. Yeah. 0, 1. So I think I made a mistake probably. 1 second. 1, 1 is going to be, 1 second. 1, 0. Where is that? 1, 1, 0. Oh, sorry. 1, 0 is going to be 2. Yeah. Okay. Any questions about this? So this would mean that the global maximum is this thing, and the global minimum is this. Okay. So now they ask you to do the same thing. The maximum of f on the boundary is this. This is greater than, sorry. That's, okay. Find the maximum minimum values of this function on this disk over here. So very similar to what we just did. We first find the critical points. So that would be the derivative of this with respect to x, which is y, the derivative with respect to y, which is x. And so the critical point in the interior of the disk is 0, 0. And we plug that in. So we make a table, x, y, 0, 0, and we get 0 for f of x, y. Now, in the interior, sorry, in the boundary, we are going to look at this boundary over here and this boundary over here. And we end up doing that by just plugging the boundaries into our function. So the first one will be f of x, and for y, we're going to take the positive part of the square root of 1 minus x squared. And we take the derivative, and this is all a Calc 1 problem. So I'm going to skip it. And when we take the derivative and we set it equal to 0, so we're going to we take this derivative and we set it equal to 0, then we will get that this is equal to 0. And so the x's, so we will have critical points over here. And the critical point will be at x is equal to 1 over the square root of 2. And then we plug that into y. And we get 1 over the square root of 2, 1 over the square root of 2. So some point here. That's another critical point. Okay, and another critical point is the negative side of that. Okay. Same thing with the second arc. We are going to plug it in and get, we need to examine the following candidates for the maximum minimum. So we get 1 over the square root of 2, -1 over the square root of 2, and -1 over the square root of 2. So same exact thing. And then we have to evaluate these points because they are part of the boundary of the boundary. So they're also critical points. So we got a list of all the critical points. That list would be 0, 0. That's the interior point. 1 over the square root of 2, 1 over the square root of 2, -1 over the square root of 2, negative, and 1 over the square root of 2. And, well, the other ones, negative 1, 0, 1, 0, and these. And then they plug them into the equation, into our f of x. And so you plug all the critical points into our f of xy, and we get that. So for 0, 0, we have 0. For 1 over the square root of 2, 1 over the square root of 2, we get a half. The other one, we get negative a half. For the negative of this square root, so the lower part of the boundary, we get negative a half and 1/2. For 1, 0 and negative 1, 0, we get 0. So therefore, the maximum value of our function is 1/2, and that happens at this point and at this point. And the minimum values are negative 1/2, and that happens at this point and at that point. Any questions about this? Okay, so here's another example. I'm going to skip it. And let's go to the, and this is the proof of the theorem of how this works, but let's go to the summary. So again, the critical points are at, we said partial of f with respect to x to be 0, partial of f with respect to y to be 0. We use this d in order to have the second derivative of test. So if it's bigger than 0, then if the second partial is bigger than 0, we have a local minimum. And if the second partial is less than 0, we have a local maximum. And if it's less than 0, we have a saddle point. And if it's equal to 0, we do not know anything. We cannot use it. In order to find global maximums and minimums, we look at the interior points and at the boundary point. So we take f on, 1 second. Yeah, the extreme values occur at critical points in the interior and in the boundary of the domain, if we're looking at some domain. So to determine the extreme values, find the critical points in the interior, and then find the critical points on the boundary. Okay, any questions about this? So if there aren't any questions, I am going to stop here. And I am going to try to post, 1 second. I don't know. Can you hear me?
Yep.
Yeah, okay. For some reason, I cannot open my entire Zoom thing, but anyway, I'm going to quit it. So if you have any questions, you can email me. I'm going to try to post the videos on YouTube. All right, have a nice day.